Hi, I'm Peter Robertson. This is Tom Hepworth. We're gonna open up today, which is quite exciting. We're from Codasip. So today I'd like to talk about a project which we undertook within the labs group in Codasip. It's a demo project to take a IMU sensor, which captures some motion data, train a neural network classification algorithm, and put that on a CPU core, customize the core, and see how much additional performance we can get out of it. Now we've got quite a lot of demos within Codasip that we've already built over the years from our field application engineers. And a lot of these demos are quite impressive. We get quite good performance out of these. And that's all well and good, but I think people would point out that our application engineers are quite experienced with our tool. So the project set out to find out what would happen or how much you could achieve if you'd never seen our tool before and you had no prior experience with customizing a CPU core. So the project ran over 3 months. Let me just go to the aims we set out. So we want to take a small, minimal RISC-V reference core. The reference core we designed ourselves. I say we didn't do it. Keith Graham over here at the front designed the reference core. It's part of a family of small reference cores we've got. I'm sure he'd be happy to take some more questions on that later. We want to see if we can maximize the performance on this minimal hardware. So the reference core itself is a single stage small core. And we wanted to just customize this, focusing on using custom instructions directly within the core itself. Take an AI workload. The workload itself is a small neural network. It's something I think is fairly relatable to small IoT devices. It's not a massive Gen AI thing. I'm not going to claim we can do that on a single stage core. But it is something small and somewhat relatable. And we just want to see how much we can accelerate that and see how much you can do with smaller hardware. And as I said earlier, we want to do this with minimal engineering resources. So on this, it was a 3-month project. It was actually an onboarding project. So I hired Tom in July, and I gave this to him. And depending on how this talk goes, he might pass his probation, but we'll see. So Tom had no prior design experience. I don't mean to slate you now, Tom, but no design prior experience. He basically came straight out of uni into Codasip and had never seen the tool before. The CPU reference core that I talked about earlier, this is part of a ultra-low energy processor family that we're currently working on. I don't know when it'll be more public, and I don't think I'm allowed to say too much, so I think I'm getting away with just introducing it here as what it is. But it's a single stage, single cycle core that is a super small area and low energy. So not the sort of thing that I think you'd expect to be able to run an AI workload. But spoilers, we've got some stuff running on it. The workload itself is an action detection model. So what I mean by that is we take an IMU sensor that takes some movement data, so accelerometer data, motion data, this kind of thing. And we train a classification model that can do classification between a simple selection of tasks. So it will classify between standing, walking, and running. So it's not a crazy application, but it's a somewhat relatable application. It might be something you might have on a smart wearable device, something a bit like a Fitbit. And with more time, you could go and capture more data of more activities and train it on doing that. But doing that stuff wouldn't fundamentally change the model itself. You'd still have a small recurrent network with a couple of fully connected layers. In total, it's below 6,000 parameters, so pretty small. And then we obviously quantize this down to int 8 and put it on an embedded device. The resources I mentioned. So myself, I'm a machine learning engineer. I don't have any design experience with CPUs. I live in Python. It's great. I'm sure you guys are all smirking at that. So I just designed the model, trained the model, and designed the data collection task. Tom, as I mentioned earlier, he did all the profiling of the workload within our tool, Codasip Studio, and he implemented all the custom instructions. Really, I should hand over to him because I didn't do that much. The tools itself, I mentioned Codasip Studio. Codasip Studio is our design and customization tool. It allows you to take either a reference design, which we've got several, or if you like, you could start from scratch and design your own CPU core. You can then explore the architecture space with applications that you might want to profile, and feed that profiled knowledge of your application back into your design, and it can point you towards some optimizations you might want to take. And that was basically the workload that Tom took. And the nice thing with this is once you implement your customizations, be these custom instructions or changes to microarchitecture, it generates a compiler for you that can use those customizations straight out of the box. Okay, so some spoilers for the rest of Tom's talk. He did fairly well, I think. Given this was all in 3 months' time, we get a cycle reduction of over 35%, which comes out to be about a 150% increase in speed. That does work. I'm sure the math works out. I can't remember how to do it now, but over 30% cycle reduction. Also about 30% power reduction and over 11% area increase. You'll never get all three of them right. But given that it's already a very tiny core, 11% is a pretty small increase. As I said, my involvement in this was quite small. So only 1 week of capturing data and training a model isn't that bad. And Tom then took the reins and took 3 months of customizing the core. And that includes all the time of going through our educational onboarding tools and learning everything. So I don't know if 3 months is really representative, but yeah, if you've never seen anything, this is what he got in 3 months. So Tom, I'll hand over to you, and you can talk over the process of profiling and customizing and all the fun stuff. Okay?
Hi everyone, thanks for coming. I'll talk about what the actual customizations I did were. So the benchmark we're running, it's a TensorFlow Lite application written in C++. We're just reading data from the IMU sensor, quantizing it, running an inference, and reading the output. We do that 10 times. So we're profiling the entire benchmark and also just inference itself, which is what I was targeting mostly with the customizations. So yeah. When you do profile it, Studio gives you common instruction sequences like this. So the top one, surprise, surprise, we're doing a recurrent neural network. So MAC comes up a lot, multiply and accumulate. So Studio will show us this, the multiply and the add, and the df0 just means it's using the same registers, and as well as a load byte post increment. So it's loading bytes because we're working on quantized int8 data, and then post incrementing, obviously, we're just loading loads of matrices. So that's about 26% of the total cycles. So you can straight away target these two areas, and there's a couple of custom instructions which are really easy to implement. So there's the MAC32, which just multiplies two sources, adds them to accumulator, and the load post increment is pretty self-explanatory. And yes, so Studio will give you a compiler which will use these instructions automatically. And this is how they get subbed in. So this is the inner loop of the gem function in TensorFlow as assembly. And you can see how the instructions just get mapped over very simply. So that was really quick and easy. And it gives us a 13% reduction in cycles per inference, and already like a 8 to 9% reduction in power for 1% area. So it's, again, really small core to start with, so it really is not that much impact on the core at all, for already significant results. Next, I want to try and do something a little bit more complicated. So there's this whole procedure here, which the profiler told me was a hotspot. So it's a common operation in quantized neural networks. It's basically just doing some saturation, a multiply, and some shifting around. But the point is, it's not mega complicated. So this whole thing was taking about 10% of the cycles per inference, and it's about 40 lines of assembly. But if you write it all out combinatorially in Codal, you can compress it down to a single instruction. So doing that and replacing the function body with this little bit of inline assembly, the 10% of the cycles that it did use pretty much vanished. So we got now a 23% reduction in cycles. And because we're not executing all of those instructions that were part of that procedure, there's a lot of power saved as well. And still not too much impact on the core, the size of the core. And obviously with GEM, there's a lot of data level parallelism, so SIMD immediately comes to mind. Because it's quantized, you can fit some SIMD operations just into the 32-bit registers of the core. I made a couple of operations. So we're loading half words with a post increment. It's basically the same as the instruction I mentioned earlier. And another one to add a quantization offset, which is just necessary for how that kind of integer-only maths works, but it's not too critical. So load half word, add the quantization offset, and then another instruction which multiplies 2 of these 16-bit pairs of numbers and accumulates them. So that gets us up to our roughly 1.6 times speed up for per inference, and again saves us a lot of power just because we're executing less instructions and flipping less bits. And so I had to add another multiplier, so there's a bit more impact, but still probably justifiable given the size of the core. So we're doing about roughly two-way SIMD. It didn't double the performance. And that's because in the inference there's loads of other stuff going on, data moving around and such. But if we look at just the inner loop of gem, this is with our previous customizations. So we're doing one MAC in about 8 cycles on these instructions. And now with the SIMD ones, we're doing 7 cycles per 2 MAC, so it's about 2.3 times speed up compared to the previous customizations. So this will hopefully let you run bigger models on a core like this and make that more accessible for small embedded hardware. So yeah, that's the progression that I followed in a few months' work. If we had a bit more time, there's loads we could do. There's other areas to target. I won't read all of these out, but I had loads of ideas for how you could keep going on accelerating the inference, and then obviously in your application there'd be other areas which you could also target with custom instructions. We've made a physical demo as well. Barath, my colleague, very kindly made an FPGA platform for the core we used, and just to prove it does actually work, we synthesized it and meets all the timing and everything, and as well we put it on TSMC 28, and yeah, it's all fine. So yeah, if you have an application like this, now you might be able to run inference at a higher rate, you get more throughput, use a more complex model and do more with your AI on this small hardware, and use less power. You could downclock and use even less power. Or you can maybe tape out on a cheap technology node and save a bit of cash. So yeah, thanks for listening. We've got a physical demo later if you want to see the FPGA platform running, and I can show you a bit about how to implement custom instructions in Studio. So yeah, thanks. I think we can take
Any questions for Peter and Tom? Going once. All right, then let's give them a round of applause. Thank you very much.